Hey, good morning, everyone. Thank you so much for coming out. What I enjoy about doing the spring series of these talks is that by the end, it actually starts feeling like spring. That's always very exciting. So thank you for being here. As always, we want to extend a huge thanks to the friends who make this program possible, and also our refreshments, which we always really enjoy. And we also want to give a huge thanks to BevCam, who come and record many of these presentations, which is always really awesome. And they have a newly opened office, I guess not too new, about a year, on Cabot Street, so you have no excuse not to visit them as well for any of your... Jesus Christ! I guess...
Silence, shut up,
part of the talk I would ask, maybe put your phones on silent if you have any.
The whole thing off.
It's okay.
I'm so sorry.
Oh, that's not to worry, not to worry.
I'm the much less important presenter. All right, well, thank you so much. We're so happy to have with us here today Dr. Stephen Young. He's a professor of remote sensing and environmental sustainability and served as the chair of geography. Oh, it's actually written here. Thank you. That's very helpful. Geography and Sustainability Department at Salem State University. Great. Don't have to memorize anything. All right. And so we're really excited to have you here to talk to us today about the science of climate change and what's going on with New England. Thank you.
Great. Thanks, Graham. And thank you very much for coming out. And thank you to the library for allowing this speaker series to go on. I always enjoy coming here. A few familiar faces. So I was riding my bike the other day, and I saw all these maple seeds on the ground. And it made me think, wow, maple trees have woken up, they stored energy from the year before in their roots, and they sent it up, and they made flowers, which actually takes quite a bit of energy. They've exchanged their DNA with other trees. They've taken that DNA, they've created new embryos, they've packaged them, they've given them wings and sent them out already, and it feels like it's the beginning of spring to me. But life is amazing. I originally was trained as a biogeographer. I looked at the spatial distribution of life around the world. And I got involved in climate change maybe 20 years ago, thinking that we're going to get it all fixed and everything, and I'm going to go back to biogeography, and I'm still talking climate. So today, I'm going to talk about why the Earth is getting both wetter, we're getting more extreme floods than ever, and why it's also getting drier. We're experiencing droughts like we've never experienced before. And my goal today is just to give you the basic science of what's happening. And then you can make informed decisions in your life around climate change. So first going to talk about the science of climate change, then a little bit about what's happening in New England, and then a little bit about the future. And the little note down there, I teach an entire semester class. At the end of the semester, I still don't think I've got enough said. So doing this in an hour, I kind of condense things. And I'm more than happy to talk with people afterwards about certain details. And partly the biogeographer in me still is amazed almost weekly at life on Earth and the beauty and the abilities of it. And climate change, being a researcher in climate change can be a little depressing. And so remembering the beauty of the Earth helps. So we live on this very, very complex world. And one of the ways to understand it, there's a number of different ways to understand our world. We can understand from a historical perspective, from a religious perspective. A science perspective is a great way. And science is a method, just a way to get an understanding of things that are happening. And it's based on observations. And I make that highlighted because that's where we get our information from. We collect data about temperature, about precipitation, about humidity, different parts of the world. And based on that information, we then figure out what's going on. There's no secret recipe. There's no secret handshakes or anything like that. It's transparent. When you publish a thing, you've got to publish how you got your data. You have to publish your data sets. You've got to show your methodology. It's totally out in the open. And everybody, other people challenge you, or they run experiments to see if what you found is true or not. So, we've got all these instruments that are collecting the data about temperature and precipitation. And the coolest instrument of them all, I think, is this thing here. It's out in the ocean, and we've got thousands of them in the ocean. And what it does is it hangs out on the surface for a little bit, then it drops down about 1,000 meters, and it's collecting temperature data, salinity, other issues. Floats around, then it drops down, and it's collecting data the whole way down to 2,000 meters, then makes its way back up, sends its data to a satellite. Satellite sends it to a receiving station. Receiving station sends it to a university or something like that. And we store that data. We know the temperature of Earth. We know the physical characteristics of Earth like we know in medicine about our bodies, right? Some of you may have had these things where they make a decision in your leg and they're doing heart surgery. It's amazing what we know about the human body. We know as much about planet Earth also with these kind of things. And we collect all that data. We've got so many sensors on land, on ships, in the water. We collect that data. And this is a graph of average global temperature from 1850 to 2024 last year. And I'm gonna spend a little bit of time on this graph. Oops, if I go the right direction. So each one of those dots is what we call an anomaly. An anomaly just means something that's different from everything else, right? And so all those little black dots are annual anomalies, how far they have moved away from something. And what they've moved away from is, we took the first 51 years of this data set, from 1850 to 1900. We added all those years together and divided by 51, and it gave us a base average. And every single one of those dots is how far it was above or below that average. And the reason why we picked this period is called the pre-industrial period. There's not a lot of cars going around. There's not a lot of smokestacks. There are some. The Industrial Revolution has already started, but that's our base. And so what we're saying is that every one of these dots represents the difference from that year, from that pre-industrial period. And what really would help this graph would be a line at that average, that 0 point. And so every one of those black dots is either, if it's above that line, it means it was warmer than that pre-industrial average, or if it's below this black line, it means that it was under. The last year it was under, I think was, I got a slide coming up, I think it was 1935, something like that. This red line that runs through the middle is nice. It's what's called the run. Earth, energy on Earth is moving all around between the ocean to the atmosphere to the land. And so you can see each year kind of bounces up and down. Rarely is it boom, 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 boom. And this red line kind of smooths out those bounces so you can get a good visual of change. So, here's a cool thing in science. We always say what we don't know as well as what we know. And these bars that go up and down, these black bars, it means that this dot actually could be as high as that or as low as that. This is the average, this is what we think it is, but because we don't have as many instruments back in 1860, we didn't have those buoys back then, so we've got some uncertainty. Notice, those they're still there, but they're almost gone, because we've got such ability now to measure temperature on Earth. So, here we see that up and down. We see this kind of red line going a little bit up and down. Here, between 1960 and 1980, pretty much in the 1970s, there was a distinctive change in global temperature. And it has just gone up. And notice that the curve isn't straight. It kind of dips and then it picks up a little bit. So that's, since the 1970s, it's been a clear signal. Actually, our climate has changed. For about 8,000 years, it was stable. It did have ups and downs, but in the 1970s, we really entered this new climate, which the driving thing behind it is warming temperatures. Does that make sense, that graph?
I don't understand why there's so many dots and under the line, only 3 dots over the line, but the line goes up.
So this dot.
No, I mean in 1960.
Within the black box.
Within the black box, there's lots of dots under the line, but only 3 dots over the line.
So this running average is taking many years into consideration, and so this. Yeah.
Yeah, I thought that he had dip, but I don't know.
If I knew, I don't know the actual number of years, but if I knew them, we could do the math and show that. Yep. That's a great observation, though. All right, here it is. So if we take the pre-industrial era as the average, anybody who was born before 1935, you've experienced the old climate. And if you're 90 years and younger, you've always lived in this new climate. Or if we take the 70s where it's changing, 1977 was the last year that it was below the 20th century average, when we took 1900 to 1999 and created that era. Anyway, we are in this new climate. So another thing in science, we often don't rely on a single data set. We often have many different data sets. And so there are these things called climate proxies. Tree rings, coral, ice cores can tell us about the past. And so each one of these colored lines is a type of climate proxy. And some are, NH means northern hemisphere, one of them is global. And the last one, that last red one, are actual temperature measurements with thermometers. And so we can see that although there are differences between these data sets, they do tell a pretty similar story. Up and down, not too extreme. And then this is our measurements. And the one interesting thing is that the measurements that we've made with thermometers match up really well with those climate proxies. And so we know that they must be fairly accurate because they do line up with actual temperature measurements. This is the year 2000. This is temperature now. And so if we look in the past, we're out of the ballpark with temperature. It's been many millions of years. Earth has been warmer than it is now, and Earth has been much colder than it is now. But the thing is, for us, we lived in this stable climate that allowed civilization to flourish. It's got its problems for sure, but now it's changed. All right. So the reason why the Earth is the temperature that it is actually a simple formula of energy in versus energy out. We get our energy from the sun. There's a little bit of energy that's still being released from inside the Earth, but 99.9999 is coming from the sun. Every body that has any heat energy radiates energy. And so the Earth radiates energy out to space. The hotter an object, the more energy it radiates. The cooler an object, the less it radiates. We've got satellites that measure how much sunlight's coming into the Earth system. We know pretty accurately how much energy is coming into the Earth system. And we know that, so here the yellow line, we've got the up and down, which goes with this cycle, the sun cycle, and the running average is that bright yellow. Earth's temperature is the red, and there's not a relationship. In fact, solar energy has been dropping slightly. Not a tremendous amount, but it's been dropping slightly, and so that's not the cause of why the Earth is getting warmer. It's not that we're getting more energy into the system. What it is we've changed the chemistry of our atmosphere with our industrial life. And there's a thing called the greenhouse effect. And we've put chemicals in the atmosphere like carbon dioxide, methane, and like the glass of a greenhouse, those chemicals actually let sunlight pass through them. And then the Earth absorbs that solar radiation, and Earth is cooler, so it sends out its energy as this long-wave radiation. And those greenhouse gases actually absorb that long-wave radiation. Just like this wall is opaque to sunlight, radio waves can pass right through this wall. So solar radiation, which is a short wavelength, passes through those greenhouse gases. The Earth sends out a longer, cooler wavelength. Those things were able to absorb it, and they re-radiate in all directions, some back to Earth. And so then the more of those chemicals in our atmosphere, the more it absorbs and re-radiates. And so that's why the Earth is warming, is because of this greenhouse effect. It's natural. Before humans ever evolved, the greenhouse effect was going. In fact, it makes life, Earth, livable. It keeps the Earth warmer than it would otherwise be. Without the greenhouse effect, Earth would be average below freezing. But we've enhanced it. We've added more to it. And so they often call carbon dioxide the thermostat of Earth, because the more carbon dioxide, the hotter it gets because of this effect. Yeah.
I thought the ozone layer was very important, and the hole in the ozone was supposed to be the thing that caused the global warming, and that was 35 years ago. The hole in the ozone layer was a big deal. I don't see ozone on that.
So, ozone is a different issue. So ozone absorbs ultraviolet radiation. So the sun sends out gamma rays, X-rays, ultraviolet, visible, infrared, and ozone, which is 3 molecules of oxygen, they absorb that ultraviolet radiation. And the issue with the ozone hole was that it was over Antarctica and some of Australia and some of South America, and you will burn with a lot of ultraviolet radiation. So the concern was for that, not with global warming. There's two different issues. And what is great about the ozone thing is the world got together in 1987 and they said, you know what, we've got a problem here, we need to work together. The rich nations had to reduce their chlorofluorocarbon use quickly because they could afford to. They came up with alternatives, shared it with the world, and the ozone hole has not gotten bigger, and it is healing itself. It's a great story of global thing, but it's different.
Oh, okay.
Yeah. I sometimes get it going off on tangents, sorry.
Yeah, I should shut up.
No, shouldn't. You know what, you shouldn't. If you get too much, I'll ask you to be quiet. And I've rarely ever had to do that. So, here's a situation. So this duck is going to hang out there if the amount of water coming into the tub is equal to the amount of water leaving. Basically, what we have done is we've stopped the energy, we've slowed down the energy from leaving the Earth system. We've squeezed the drain pipe. And so the Earth was filling up with heat. The groundwater is filling up with heat, the lakes are filling up with heat, the rivers are filling up with heat, the oceans are filling up with heat. The entire Earth, just like this bathtub, is filling up. Not equally, the Arctic regions are filling up faster, but that's basically what we've done. And not only do we have satellites that can measure how much incoming solar radiation, this is a satellite image, or this is a combination of many satellite images of Earth's energy being sent out to space. And so we know very well how much energy we're sending back. So we've actually calculated how much extra energy is being stored on Earth because of the greenhouse effect. And this is probably 5 years old. it's increased. So we know science is observations and mathematics, and we know exactly how much extra heat we've got. And we know where it's going. It's mostly going into the oceans. So that's one reason why we don't really feel it and we don't really feel the urgency, is because it's being stored in the oceans. And the oceans are vast. They're like batteries. They're storing this energy and they're starting to release it. The hurricanes have gotten pretty intense. Storms have gotten pretty intense because of that heat. There's mass migration going on in our oceans. I don't have a slide with me for this one. I had to actually go through and ditch a lot of slides because sometimes I do too many. But lobsters, which used to be quite prevalent in Long Island Sound, are not down there anymore. They're migrating. Yeah. All right. This is another really cool thing about science. We're going to look at the past. So I forget what the exact number is, but it's something in like 95% of all fresh water is frozen in Greenland and Antarctica. So there's a lot of frozen water. And and a million years ago, it was snowing in places. And so we can drill into Antarctica, into Greenland, into glaciers, and go back in time and see what the environment was like. It looks like a lot of fun. So here are these cores, and we've got refrigerators all over the place storing these cores and doing more and more of them. And what's kind of cool is so the snow lands and stays there. The more snow comes down, eventually it gets compressed into ice. And there was some air pockets in there. All the air wasn't pushed out. And so we've got these bubbles of atmosphere back 500,000 years ago. We know the chemical composition of the atmosphere. And there's a thing with oxygen molecules. They're not all the same weight. And when there's a lot of energy on Earth, heavy oxygen molecules can get evaporated. When there's not, heavy molecules don't get lifted up. And we can use that without going into detail, since it is a whole week lecture in my class. We can tell the temperature of what it was like back then as well. Very, very, very precisely. And so this is an example of what we get. Here is years before present. So here's pretty much today. And this is 422,000 years ago. It's from the Russian research station in Vostok in Antarctica. And so carbon dioxide levels from those bubbles are in orange, and the purple is temperature. What do you notice about the relationship between temperature and carbon dioxide?
I see it happen again and again and again.
Yes, yes. They rise, they fall, they rise, they fall, they rise, they fall. They rise together. They're very closely linked to each other. Aside, another week's lecture is, these are different eras of the Pleistocene, and the Earth, actually, its orbit goes from elliptical to circular over a 100,000-year cycle. Also, the Earth itself is wobbling in space, and one wobble takes 44,000 years. And when Earth wobbles, the amount of sunlight we get changes. And so it's that orbital pattern that creates those different eras in glacial periods. It's the gravity of the other planets and stuff that actually changes the Earth's wobble and orbit. But the key thing that I want you to get from this is that those two are related to each other. And here's another one. This way we separate this out. Here is today. This one goes back 800,000 years. This is temperature. Oh no, this is carbon dioxide. This is temperature. And so we can see we measure carbon dioxide in what we call parts per million in the atmosphere. And here we are today. Right, this is 800,000 years of our atmosphere, based on observations, based on what we found. We're out of the ballpark. And unless the laws of physics change, temperature is going to rise. It doesn't happen right away. It's like investing in a CD at the bank. Over time, you make more and more money. Over time, carbon dioxide makes it warmer and warmer and warmer. And carbon dioxide molecules naturally stay in the atmosphere for about 1,000 years. And so that's why it's also a concern. It's what we do today really influences the future. Okay. This is I grabbed this the other day, May 5th. We measure the chemical composition of the atmosphere. A graduate student in 1958 got a grant to go to Hawaii and set this thing up on top of an old volcano because it's not near much human activity or anything. So we get a nice clear picture of atmosphere. And so this shows carbon dioxide. And photosynthesis in the summertime in the northern hemisphere sucks carbon dioxide out of the atmosphere. And then when the leaves drop and the detritus decomposes, that carbon dioxide goes back into the atmosphere. So that's why you've got that up and down. But the increase is due to human input of carbon dioxide to the atmosphere. And it keeps going. Last year we put more carbon dioxide than we ever have in human history. It has not slowed down. And this is methane. It kind of flattened out in the early 2000s. Then we discovered fracking, and it's gone back up. Methane doesn't stay in the atmosphere as long, but it's more powerful than carbon dioxide. So this station that was set up in 1958 in Hawaii, and it runs pretty automatically. A lot of our data collection stuff is automated. And it gives this long data set to the world. DOGE wants to shut it down to save $100,000 a year. They haven't been able to do it yet, but we will stop knowing what the chemical composition of our atmosphere. We have other sites, but with science you want to have you want to remove as many variables as you can. Yeah. It's so the Intergovernmental Panel on Climate Change are a bunch of international scientists that get together and create these reports. They don't do the research, they look at what other researchers have done and they synthesize it. And they're like, if we really need to try not to pass 1.5 degrees Celsius global average temperature, and for a long period. And we did just pass it last year. Temperature may come down for a while. That right, it's got that up and down pattern. We're not sure, but we are pushing the limits. And at 1.5, more and more almost apocalyptic things can happen, and I'll explain why. And when it gets to 2 degrees Celsius, if it gets up there, some irreversible things will happen, like ice will not come back. We'll pass these tipping points. So in response to this, a lot of places have a lot of local places, states, countries have said, okay, we are Salem State, City of Salem. We're gonna do our best to try to be carbon neutral by 2050. And to do that, the blue line is each year's amount of carbon dioxide the world puts into the atmosphere, and if we're going to do that, we really do need to start to turn that curve. Okay, review. As I tell my students, if I spend a lot of time on something, or if I do a review, it's probably going to be on the quiz. And I don't know if Graham told you that you've got to take a quiz before you leave. And for every question wrong, you've got to donate $10 to the library. So we clearly know the relationship between temperature and carbon dioxide. And science, we do experiments. There's this cool experiment where you've got this tube. And on one end, you've got a calibrated heat thing, and on the other end, you've got a sensor, and it's a vacuum. There's nothing in it. And you slowly put carbon dioxide molecules into it, and you can actually measure how much heat does not make it to the other side. And so not only ice cores tell us this, but experiments tell us this. It's very, very clear. And Because of our observations and measurements of the atmosphere, we know that carbon dioxide is increasing into the atmosphere, and we know it's related to the temperature that's going up. So that's the first half. Here's another graph, and I love graphs. This is the atmospheric capacity to hold moisture. Our atmosphere is flexible. There's molecules constantly leaving the atmosphere, going into the ocean into the atmosphere, into human life, out of human life, and also moisture goes in and out of the atmosphere. But there's a limit to how much moisture the atmosphere can hold. When the atmosphere is cold, so this is temperature in Fahrenheit from 0 to 120, and this is how much the air can potentially hold, what's the maximum amount of moisture can hold. And when it's cold, the air can't hold much moisture. There's an old saying, too cold to snow. Well, it's true, because when it's so cold, when it gets to like -20, there's almost no moisture whatsoever in the atmosphere. As the temperature increases, the amount of moisture the atmosphere holds increases, and it doesn't do it linearly. When I say linear means 1 foot in, 1 foot up, 1 foot in, 1 foot up, 1 foot in, 1 foot up. We're used to that. Our stairs are that way. A lot of things in our life are that way. This is exponential. So when I increase the temperature from 20 to 40 degrees, the amount of moisture the atmosphere can hold is this much. When I go 20 degrees from 80 to 100, that's how much the atmosphere can hold. Also, not only that, but as the atmosphere warms up, its capacity to hold moisture increases, but also it has more energy. And when the atmosphere is sitting above the land, that energy goes into evaporating water. And our atmosphere right now is a little bit like a vacuum cleaner on low. It's sucking moisture out of the environment, and it can hold it longer, so some regions will be dry. All right, so the relationship, increase in carbon dioxide, increase in temperature, increase in capacity to hold moisture. And science, we measure things, we make observations. And this is how much moisture is in the air. We call it total column of water. And we can see, and again, these are the anomalies. Or no, this is the total capacity. These aren't anomalies. These are the total capacity. And we can see that over time our atmosphere is actually filling up with air because there's more room up there for the moisture. My area of expertise is satellites, and this is a satellite that measures it. Areas that are decreasing, atmosphere that's decreasing in moisture is in the brown, increasing is the green. Most of it's green. There are a couple of brown places, but we are observing that, in fact, our atmosphere is filling up with moisture. And some of the results are droughts. And we're seeing these big and small droughts around the world. Last year, that's the fires in Lynn Woods. We were hit by a pretty strong drought and fire. And there's a little walk I do near my house, and there's some vernal pools. And even though we've had a lot of rain lately, they're pretty small. So we're still pretty dry here. Here is a graph of observations again. And so the red means there's a drought of 6 months or more. The yellow, yellow is 3 months, and the gray is 1 month. Here's that period that we saw the temperature kind of change in the 1970s, and the world is getting drier in a lot of places. There's no question about it. And areas especially hit are what we call semi-arid, because there's enough moisture to grow some grass, to grow some stuff. But trees aren't going to grow there because there's not enough moisture. Those areas are turning to deserts. And other areas that are productive, like us, we get hit with drought also. It's observation data, right? And LA was hit with 2 years of excessive rainfall. And so because there's lots of sun and it's warm, life just boom, took off and created all this all this material. And then for 8 months, it didn't drop, not a drop of rain came, and everything dried. And that warm atmosphere, right, sucking the moisture out of all that vegetation, it was apocalyptic. Floods, right, the one in Spain, that was totally not prepared for that. I was up in the Northeast Kingdom in Vermont last summer, and roads almost completely washed out from short flash floods. We're seeing what's called 1 in 1,000 year floods, when that means in a normal period, our past climate, we would see this flood in about once every 1,000 years, and we're seeing it more frequently in a lot of places. And not only so, right, the atmosphere can hold more moisture, and then when it does release it, when it hits a cold front or something and it gets really cold and it physically can't hold that moisture, it lets it go. And we're seeing, this is a graph of intense rainfall. And so we take this period in the light gray, that's our average, our base period, and then every point on this line is a year relative to that base period. And we're getting rain in harder rainfalls than in the past, according to the observations. And it increases erosion. It doesn't infiltrate into the soil as much. It runs off faster. The Gulf of Maine, using satellite imagery now, has more silt in it because of this heavier rainfall in New England. And more silt means light can't get down as deep into the marine environment. And here's one that's gonna bite us somewhere, is insurance rates. I have a friend who got so fed up in Swampscott and they canceled, and then they tried to get another insurance. They couldn't get anything as cheap. And there's a strong correlation between the price of national disasters and the price of homeowners insurance. And in the 90s, the organization that was most concerned about, other than the scientists, about climate change was the reinsurance agencies that insures insurance agencies, because they saw this coming. Just the other day, NOAA was told they cannot estimate the dollar cost of disasters anymore in the United States. That we're stopping that data. So we don't know if disasters are becoming more expensive or not. So a couple years ago, Jia Chang was a master's student of mine, and we did this a study about flooding in Shanghai, and she wanted to do 1 in 1,000 and 1 in 5,000 year floods, and I thought, how ridiculous! This was back in January of, I'm going to say, 2020, COVID time. And now I see it published all the time that what I thought just a few years ago was crazy with flooding. Now I see it. All right. Changes in New England. So I wrote a published paper with my son Joshua on overall warming with reduced seasonality, temperature change in New England from 1900 to 2020. And there's a lot of weather stations around the country. And these are weather stations that go all the way back prior to 1900. And they also haven't moved the equipment around, because when you move equipment, you change the environment that they're in. So these are well-calibrated stations of temperature. And so we took those and we looked at change in seasons and annually, and we found that, and we used Celsius. That's what we use in science, and I don't know if it's still true or not, but you know the similarity between the United States, Myanmar, and Liberia? The only ones that use Fahrenheit, right? And we're a big anomaly. We'd be way high. Anyway, every season's warming, and the season that's warming fastest in New England is the winter time, and the minimum temperature of the winter time is warming the fastest. So heat always goes to cold, And that's why. And that's another reason why we're not so concerned. Who does not love a warm day, March 10th, right? I love it. And I'm like, damn, it shouldn't be this way. But so that's heating the fastest and also making us more complacent about our situation. But all the seasons are changing. 3.2 degrees Celsius is 5.76 degrees Fahrenheit. And so each winter day is about 6 degrees warmer at the minimum than it was back in the 20th century. And here's a graph of this is global temperature. This is New England. And you can see New England's got these long bars because we don't have a lot of sites, where the globe has an incredible number of sites, so they've got less air. 1960s, the air was so polluted that temperatures dropped. It was called global cooling. It happened in Europe, United States. That's why New England's temperatures dropped. But since that period, when these error bars do not cross each other, it means they are completely statistically different from each other. So we're warming faster than the world average here in New England. And Massachusetts is warming faster than the other New England states. All the New England states are especially warming in the wintertime. So there's my son, and he and his other brother came home from college, and I'm like, hey, let's do a science project together. And one of my sons said, no, I'm going to play video games. But Joshua, he's in linguistics, and he was really into data and stuff, so he was my data guy. And our results were so amazing to us that we then published it, and then got on the front page of the Boston Globe. That was fun. Sometimes it can be fun. So some of the reasons why we're warming up, first of all, places with high latitudes are warming faster than places with low latitudes, especially the Arctic region. Arctic region is warming twice as fast as we are. And another thing is the ocean. Remember, the ocean's absorbing all that energy. And a lot now, we're starting to see a lot of that energy begin to surface. These heat blobs. And Gulf of Maine is, what's happened is the Gulf Stream, which comes by here, has actually been pushed further up to the north where it used to be cold. And so it's starting to get warmer in the oceans off of New England. And so that's where we're getting some heat from. Snow cover. Snow cover is another thing I look at with satellites. So I look whether there's snow on the ground or not snow on the ground, and what's the temperature of the surface of the Earth. And with a graduate student, we did this paper. And the importance of it, the reason why we did it is because when there's snow on the ground, sun reflects and goes back out to space and doesn't stay here on Earth. When there's not snow on the ground, a lot of that solar energy gets absorbed and stays on the Earth system. And as we decrease in snow cover, we become less reflective, and so more of sun's energy is staying. So because of the change in snow cover, we are actually increasing a little bit of that incoming. Remember I said there's no increase? It is increasing a little bit because of our changing of what we call the albedo, or the reflectivity of the Earth. And so our study questioned that, and what we discovered is that in the northeastern North America, snow cover is declining really fast. In some places it's increasing, but mostly it's declining. And there is a very close relationship between decreasing snow cover and increasing temperature. They've got a strong inverse relationship, which means that as the snow disappears, the sun's not reflecting, it's being absorbed and getting hotter. And that's one reason why our winters are warming faster than those other seasons. It's all related to each other. I did another study with snow, and I looked at the whole world. And again, I found globally snow cover is declining 10 times faster than increasing. Between this period, about 5% total amount of snow cover disappeared. And then there are these hot spots of decline. The world is not even, and one of the hot spots is here in New England. The area of red is snow cover is being lost faster than 95% of the rest of the world. The pink is 90%. And one of the reasons is we're at the far southeast part of the snow cover of wintertime. And we're on the edge. So the edges are melting back. And we happen to be in one of those places where that's happening. Yeah, there maybe some of you might have been from Connecticut or something. There used to be snow hills down in Connecticut, local ski things. There's been a lot of literature of all the small ski places disappearing because of climate change. This is the only slide I have about this. So that snow data that I use to get an idea of what's going on in the world is being shut off. Right now, science is based on observations, and a lot of our observations are automated, and we want to have continuation of data. Anyway, I got an email that all the snow data is being shut down, not available. All these different data sets. One thing that still does, but just to make me really proud of the United States. I've worked in China. I've worked in 15 different countries in satellite imaging and stuff. And we're the one country that has always promoted data-based information and shared our data. China, you'd have to buy data from different departments in the same organization and stuff. But the United States always made this incredible data available. And cynics say they made it so available because other countries will be dependent on us. I don't know. But now we're shutting these things down. I don't know how that helps us be blind going forth in the future. And I know what's going on in medicine and in other areas as well, but this is my only slide about that. So, what's happening in New England? Precipitation's increasing because there is more moisture in the air. It's coming heavier. We're getting more floods, so more erosion, less infiltration. It's increasing in the winter time, and the rain to snow ratio is increasing, which means it's more often rain than snow. And if you think about it, it used to be 6 degrees colder. And so now it's 34 and it's drizzling, where in the past it would have been snow. So many of the rain showers we get now are near the freezing point. The weather whiplash, right? It goes hot, cold, wet, dry, and not just from day to day, but also month to month and year to year. There's some research that looks at that, and the extremes have increased as we've gotten. Summertime, we're estimated to get similar amount of precipitation, but because it's warmer, there's more stress. There's more evaporation happening, less, when the storms come, when the water comes, it comes heavily. So that's a long-term prediction. And here's data about change in annual precipitation of the last 30 years compared to the 20th century. So we took data from 1900 to 1999 and made that the base period, and we compared the past 30 years, and you can see the greens are heavier rainfall annual precipitation, the amount of precipitation, and the brown is less precipitation. The Southwest is in a long-term drought, one of those few places that annually get less rain, and we're getting more rainfall. Again, observations. Our future. Good, I'm almost done. So a student recently said, why are scientists all of a sudden interested in climate change? The first published paper about calculations of global warming from CO2 was in 1896. Scientists have known this for a long time. It's not new. Politicians have known it for a long time. 1965, there's this environmental report that talked about climate change. LBJ noted that. We knew politically about climate change in the 60s. 1988, Jim Hansen, the main meteorologist for NASA, goes in front of Congress and says, you know, scientists are 99% sure that the heating we're seeing is caused by these greenhouse gases, and we need to eliminate those gases as fast as we can. 1988 or 89, I forget, Time magazine made Earth Planet of the Year, you know, like Person of the Year. There was a lot of environmental awareness and concern about climate change, but there was a concerted campaign started in the 1990s of disinformation and anti-science, and it's gone extreme, where it's not just climate, it's all areas of science. Final review. What's happening today is we're putting more gases in the atmosphere, and we know the relationship between carbon dioxide and temperature, and we can see the effects happening, and we know about the atmosphere, and that's why some places are getting these torrential rainfalls and floods, and why other places are getting droughts. And you can see what the future holds, because there's no sign of this slowing down. And unless we're wrong about physics, this is going to continue to happen. I'm proud of my college, my university. We've divested from fossil fuels. We're carbon neutral goal 2050, putting solar panels on all our buildings, LEED certified buildings. We're doing geothermal. We're going to try to decarbonize North Campus, and it's going to start this summer. And geothermal is going to be a big part of it. Our library also already has geothermal. We've got EV chargers on campus, bikes. We do a lot of, we've won a lot of awards for composting for maybe 20 years from our dining halls. My department, we teach geospatial skills to students about how to study the environment, how to help bring solutions. We've got some outreach that we do to the community. We're heavily involved, Marcus Luna, heavily involved in climate equity, which is a huge concern of young people today who are facing this future. Yeah, our future. It's arrived now. The key thing is, we had a stable environment for for 8,000 years, and we figured out how to live in it really well. But the system that allowed us to live in it really well is detrimental to an unstable climate, right? Farmers, right? For a long time in Iowa, we knew we could plant corn in this field because of the precipitation and temperature. We don't know anymore because of the changing temperature and precipitation. And I didn't get into it, the pests and all the other things that are happening. This is just one of a number of things happening, and yeah, it's our economic system is it. You know, I know 2 years ago the most profitable companies in the U.S. were the fossil fuel industries, and that's the thing that's driving this. And yet our economic system has got priorities set differently. Anyway, that's my talk, and sorry for diverging a bit. I hope that you have a good understanding of the science of what's happening right now, and make decisions in the future based on that information.
Where is that tree?
In Long Island.
Amazing.
Yeah, it's beautiful. I had that on something beautiful. Yeah. Anyway, all right. Thank you very much. So, questions.
We do as concerned citizens to help the Earth?
Well, you know what? I would love to turn it over to Elaine, who is head of the Marblehead Sustainable Marblehead, and I'm the scientist, and I think she would be super. Do you want to talk about a few things? Is that okay?
Yeah.
Okay.
Brief. Thank you so much. This was incredible.
Oh, Elaine, I can just grab you the microphone.
Oh,
here.
sure.
I just want to make sure everyone can hear.
That's good.
It's so great to hear the science, and it's so important, the data collection that Stephen has done and his colleagues, really to bring this information to light. So thank you so much.
You're welcome.
Just really quickly, so yes, I'm the director for Sustainable Marblehead, and we are doing some really great things over in Marblehead, and here in Beverly, Green Beverly is doing some really wonderful work too. So, whichever community you're in, look them up and see. But to quickly answer the question of what you can do, there are a lot of things you can do. I would say the biggest bang for your buck would be to take away the fossil fuels from your homes. In Marblehead, we did a study, and the carbon emissions, the largest piece of the puzzle is heating our homes. So really, if you have oil or natural gas, those will be your best ways to really make a significant difference. And there have been a lot of rebates for homeowners. I'm not sure how things will shake out, but if you're on Mass Save, if you go to Mass Save, there's a lot of rebates, so check those out. Sustainable Marblehead is going to be launching a energy coach program, which is going to be free for anyone in Marblehead to help you walk through that process, which can be kind of complicated. But besides doing the big things or switching, to an electric vehicle, every small thing you can do does make a difference. Composting, as Stephen said at Salem State, they're doing it. That's reducing methane in the environment. You can do that for free. You can walk more or bike more and drive less. You can use less plastic because the plastic has a tie-in with the oil industry. So every little thing, try not to feel hopeless. It's very difficult, but from big things to small things, these are all within your, if you feel a little bit more sense of power, just to do these small things, it'll help you make a difference. And just know that you can do things. And please check out the different websites for some ideas. So thank
Great.
you.
Thank you.
Oh, I guess you're loud enough.
Other questions? Yeah.
All your science is based on the atmosphere and the land, and they're doing great studies out of the University of Arizona for the ocean
Yes,
in Antarctica with the clam that lives 100 years, and
Right.
they're doing dissection so they can read it like tree rings.
Right.
Do you think DOGE is going to do away with that college grant?
I don't know. I don't know. Yeah, it's hard to tell.
Yeah.
But a lot of things like that are happening. Anyway, yeah. Any other questions people have? Yeah.
Just to reflect on the previous question, NSF's budget has been cut by 55%. And NIH's budget has been cut 40%. But my question, would you care to comment on the role of changing ocean currents and occasional volcanic activity on either the anomalies or other factors in your data?
Yeah. So volcanoes, they in the short term, they cool the earth. They put up lots of ash and particles, aerosols into the atmosphere. And Mount Pinatubo in 1991 put so much that global temperatures declined a little bit. Long term, they put carbon dioxide into the atmosphere, a natural form of carbon dioxide, and so long-term heating. And I don't know the specific theories, but there are certain theories of time periods in Earth's history when there was a lot of volcanic activity that would lead to warming periods. And ocean currents, I'm more of a land person and more of bioland, but ocean currents are there's surface currents, right? And there's undercurrents, and there's currents that go up and down, and the salinity and the temperature of the water determines whether water is dropping or rising. And I do know with the warming of the oceans, it's changing ocean currents. And there is the possibility of the Gulf Stream, which passes us here, slowing down and maybe even stopping, which ocean currents move a lot of energy around the world, and that would change some regional stuff for sure.
I have a question about trees and the role that trees play.
Yeah.
So I've recently heard that they might open up more public land to deforestation. How do you think that's going to affect things?
So actually, you mean like solar panels and stuff like that?
No, just like out west, I've heard that they're, going to open up.
Forestry.
Yeah.
Forestry. In New England, the forests are being opened up for logging and stuff. And so, I don't know how it's going to play out, but, we rely on a lot of timber from Canada, and that's become more expensive. And so we have a lot of timber in America. So areas are going to be opened up. And the key thing about trees, through photosynthesis, they pull carbon dioxide out of the atmosphere, and then they store it in their wood. Those trees out there, you knock on that tree, that used to be atmospheric carbon dioxide, and that tree turned it into a solid, took a gas to a solid. So that's why trees are so important, because they're storing a lot of carbon. And with losing trees, we lose that carbon storage. I just finished a paper with a graduate student, and we looked at solar farms in Massachusetts and Worcester County, and 50% of the solar farms put in Worcester County were total deforestation to build the solar panels, and another 11% were on scattered tree area. So we've done a misincentive. We need to solarize, absolutely. We need to green the grid, but we need trees also. So we're going to bumble, but it doesn't mean we're not going in the right direction.
It's such a catch-22. You don't use the plastic bags, so you're going to use the paper bags. So you got to cut the trees down to do the paper bags.
Yes, it is a Rubik's Cube.
Carry a reusable bag.
That's one solution. Yeah.
You had a graphic up there from Mauna Loa.
Yes.
I visited 15 years ago.
Nice.
I lived on the side of Mauna Loa.
Nice.
And he used to joke that they could tell their weather a couple of weeks previous if it was in China. I'm wondering how much that graph was influenced by what's going on in China now, where they're building coal-fired power plants left and right. And also to add to that, what other countries besides China are putting all this CO2 into the atmosphere?
So you know what's interesting? Yeah, China for a long time has been the main source of greenhouse gases and coal power. But recently, they've put more wind than the rest of the world combined. They've put more solar than the rest of the world combined. And there's estimates that next year they're going to start to put less carbon dioxide in the atmosphere, even though they're still building some coal power plants. I'm not sure if it's going to happen, because in our world right now is AI and cryptocurrency, which are energy hogs. And I know China's pushing with AI, so whether they're going to have enough energy, because AI takes a tremendous amount of energy, but they really have they've changed the game. Almost half of all the cars are electric in China now. Yeah, and I just got back from Kazakhstan. I was there this spring working at a university, and so many of the cars are Chinese electric because they're cheap and they're efficient and they work, and so other parts of the world are moving ahead in decarbonizing. And China's one that's flipped. Yeah, it's surprising. Yeah. I lived in China for years, and I still do work with Chinese colleagues and stuff, so I'm familiar with that stuff. Yes?
It's not a question, but it's a comment. Way back with Governor Patrick and Mitt Romney, that time they put these LNG, liquefied natural gas, before the ports off of Beverly and Marblehead. And the data said that they would increase the temperature of the seawater by 1 degree centigrade. And because they're taking the water from the seawater, heating it up so they can liquefy, they can gasify the liquid natural gas, so they can put in a pipeline. And they're like putting factories out in the ocean, increasing the temperature of the water. And that, the governors of both, the Republican Romney and Deval Patrick, could have stopped it by saying no. But because there's a demand for energy, and methane, liquefied natural gas is methane.
Right, right.
So if there's a
right.
leak from those pipelines, you're getting methane, which is worse than carbon dioxide.
Yeah, there's a lot of methane leaks.
So why
yes.
are we doing that to our oceans? Which is
Because we have an economic system that works beautifully in a stable climate. And we haven't realized that some of the stuff that we're incentivized to do is not good. We're in a transition period, and the science is clear. It's trying to, I don't know how much inertia to right the boat of our economy and our society.
Can you talk about potential effects on agriculture?
Yeah, the Southwest is under this incredible drought, and Lake Mead is going down. And Arizona, the great thing about agriculture in Arizona is there's so much sun, and there's some fertile soil. It just needs water. And so we've been growing all kinds of crops in Arizona, in the desert, and being very productive. We even grow grass for cows in Saudi Arabia. I mean, and we're running out of water, and so they're going to have to change the way they irrigate. They're going to have to change the type of crops that they grow. They're going to have to change, and there's the urban-rural battles kind of going on. It's going to be a messy thing, but that agriculture is going to change, and then along the supply chain, there's going to be disruption, and that's just one state. Where it's changing.
What about the water table, like in California?
Yeah, so the water table, water inside the earth. I read an amazing study the other day that said that our warmer atmosphere, right, is evaporating more water into the atmosphere, and more of that atmospheric water is going into the oceans and back on land. So actually the world is desiccating a little bit. And some places, are like in the Midwest, the Alagaga aquifer, I'm not sure if that's correct pronunciation, we've been pulling so much out for agriculture that water table has been going down and not being replenished in a lot of places. Yeah. And some places will get more rain, and yeah, and it's a little bit like Russian roulette, because like in Vermont, it was a small pocket of maybe 50 miles this way and 50 miles that way. They got a 1 in 1,000 year flood, and almost all the streets and stuff were wiped out of that little village that does not have a big economic base, and other villages didn't get it. Next year is going to be a different village, and do you prepare by spending all this money in infrastructure? It really is the haphazardness a little bit of it right now is like Russian roulette. Yes?
Just going to say, one of the big problems also today is people don't believe in science.
Yeah.
They just don't believe in science, the empirical data.
Until they get on a plane.
Yeah, right.
So if you, a couple ways to stop things. One is kill the messenger. If you can't argue with the message. So Al Gore, when he came out and talked about the science of climate change, they went at him. Another thing is create doubt. Because we all have a little bit of doubt in us. We all don't want to believe that it's just going to keep getting warmer and warmer and warmer, and it's not going to go back to how it normally is. We kind of want, because it's going to cause us to change and stuff. So there has been an active campaign, very, very active campaign. There was the doubting the science of cigarettes causing cancer, which delayed for 20 years, action happening, and it's been put to fossil fuels. They don't outright say no, but in the late 70s, early 80s, ExxonMobil had a science crew that did climate change. They published, and what they predicted would happen in the year 2000 came true. They were right on, spot on. They got fired after they came up with these reports. ExxonMobil increased the height of their oil platforms for future sea level rise. Tillerson went to Russia and said, you know what, the Arctic is going to be available in the future, and we're going to help you tap into that natural gas and oil because we know it's going to warm up and it's going to be viable. It became viable, and Tillerson's one of the few non-Russians to get a special award from Putin for being helping Russia tap its natural resources based on climate change information from the 80s. I sometimes need to bite my tongue.
You know, that slide said we have a decade to reverse things, but we're talking about like some companies who are going to be carbon neutral in 2040 or 2050.
I should get rid of that sign, but there are right now. Here's a question. Does anybody know Taylor Swift? Does anybody know that Taylor Swift has a boyfriend who's a football player? Does anybody know the publication by 10,000 scientists saying we're in trouble? And this is a warning to the world that we need to get our act together, right? What we hear in information sometimes, when I lived in England for a while, and they said about Americans in news, Americans are the most entertained and least informed when it comes to what's going on in the news.
European, they know.
But anyway, I'm not sure why I went off on this tangent. So some scientists are saying that, you know, there are under the Pacific, North Pacific and North Atlantic, there are these what they call methane hydrates, this frozen methane at the bottom of the ocean. If they melt and come and be this boom of massive methane, there's stuff like that that's lurking.
Also the permafrost.
Permafrost is melting. Yep. Yeah, when I was in Kazakhstan, I worked with the glaciology because it's the Tian Shan Mountains, and they showed me pictures of the changing permafrost quite rapidly.
So 50 years from now, will we be able to grow corn and wheat on Greenland?
Maybe.
So do you think it's a good buy?
Yeah, I'm staying out of that question.
But it is melting, right?
Oh, Greenland is melting, and that's why the seas are rising. And one of the recent papers I did was with the House of Seven Gables, and they're already feeling the effect of sea level rise. Right. And the paper was all about how they're going to move the houses. They're going to take the parking lot and get rid of that, and they have to move from the coast because they're being affected by sea level, and a lot of that is from Greenland. Mm-hmm. Yeah. So. All right, I've made you stay longer than scheduled.